Welcome back to the Explainer. So today we are going to break down three super important water distribution systems. These are ones you absolutely need to know for the area exams. We're going to talk about how they work, the good, the bad, and most importantly, when to use each one.
I mean, it seems simple enough, doesn't it? You just turn on the tap and boom, water comes out. But getting that water exactly where we need it, especially in, say, a skyscraper, well, that's a whole different story. It's a constant battle against, you guessed it, gravity.
And honestly, that's what it all boils down to. The whole story of water distribution is just pressure versus height. Can you get enough oomph to push that water up against gravity? Every single system we're about to look at is just a different game plan for winning that fight.
All right, let's jump right in. We'll start with the most basic setup you can imagine, a simple low-rise building. This is our starting point, what we call the direct supply, or more commonly, the upfeed system. And yeah, the name pretty much says it all. This is the most straightforward system you can get. It completely relies on the pressure coming from the city's water main to do all the heavy lifting. We're talking no pumps, no storage tanks inside the building, just pure, raw city power pushing that water up. So you can picture it like this. It's just a one-way street, right? From the main under the road directly to your faucet. The city's water supply is basically this giant, invisible pump for the entire area. And our little building is just hitching a ride on that energy. Okay, so for the ARE, here's the big takeaway. The upfeed system, it's awesome for smaller buildings. It's cheap, it's simple, there's not much to maintain. But, and this is a big but, its Achilles heel is that it's completely at the mercy of the city's water pressure. The source material mentions that pressure can sometimes only support a 20-meter head. Now, head is just a fancy engineering term for how high that pressure can push water vertically. So if that's all you've got, 20 meters is your absolute maximum height. Game over. So what happens when your building design goes past, say, 5 or 6 stories? Right, you've just hit the literal ceiling of what an upfeed system can do. The city pressure just isn't going to cut it anymore. We need a whole new playbook. And that's where we bring in the indirect supply system, which everyone just calls the downfeed system. The whole idea here is pretty clever, actually. It's like, okay, if we can't beat gravity going up, let's make gravity our best friend on the way down. The magic ingredient here? That transit water storage tank. This one thing changes the entire game. So instead of trying to push water to every faucet directly from the street, we do something different. We send all the water to one big holding tank. And yeah, you'll almost always find it sitting right on the roof. So we use our pumps and our electricity for just one job, one big push to get that water up to the roof, to win that initial fight against gravity. But once it's up there, we let gravity take over. It becomes our workhorse, pulling the water down and giving us nice, steady, reliable pressure for every single floor below. And the best part? Gravity works for free. And this really lays out the trade-off, doesn't it? We've totally solved the height problem. We can go as high as we want now. But the price we pay is more complexity, a higher cost, and a huge structural load. I mean, think about it. A giant tank full of water is incredibly heavy. The building's entire skeleton has to be designed from the get-go to handle that massive weight up top. Now, this system has a few other key players you got to know about. See those pressure-reducing valves, or PRVs? They are absolutely critical. Just imagine, water falling from the 50th story. By the time it gets down to the 5th floor, it has a ton of pressure built up. Without a PRV to tame it, your bathroom sink would basically be a fire hydrant. Then you've got booster pumps. They're for the top couple of floors, the ones that are actually too close to the roof tank to get enough gravitational push. Kind of ironic, right? Okay, PDD exam takers, lean in for this one. This diagram is something you'll definitely want to recognize. It's a classic PRV setup, and you'll notice there are 2 of them, side by side. Why? It's all about redundancy. It's a backup system. That way, you can take one offline for maintenance without having to shut down the water for that whole section of the building. It's a really smart, critical piece of the puzzle for safety and just keeping things running smoothly. All right, that brings us to our last scenario. So we figured out low-rise buildings with good pressure and high-rise buildings. But what if the city pressure is just awful? I'm talking so weak it can barely get the water to the ground floor, let alone anywhere else. This is exactly where the pumped upfeed system comes to the rescue. You might also hear it called a sump and pump system. It's built for one specific job, to work in places where the city main just doesn't have the muscle to get the job done, at all. Now, the key difference to remember is this. With the downfeed system, we pump the water once up to a storage tank. Here, with the pumped upfeed, the pumps are working all the time to pressurize the pipes directly. That's a huge distinction. And that little guy, the hydropneumatic tank, its job is to act like a little pressure cushion. It keeps the pressure stable so the pumps aren't constantly kicking on and off every time a single person washes their hands. It saves a ton of wear and tear. So this system is a real powerhouse. It solves a huge problem, but it has one massive vulnerability. It lives and dies by electricity. The pumps need power, period. If the power goes out and you don't have a backup generator, well, your building has zero water pressure. Nothing. Nada.
All right, time to bring it all home. When it comes to the RE, you've got to be able to look at a situation and quickly know which system fits. So think of these next couple of slides as your ultimate study guide, your cheat sheet, if you will.
This chart really boils it all down, doesn't it? It all comes down to asking two simple questions. 1, how tall is the building? And 2, how good is the city's water pressure? If the pressure's good, you go with upfeed for short buildings and downfeed for tall ones. And if the pressure's bad, it's almost always going to be a pumped upfeed system. It really is that straightforward.
And here we have the big trade-off for each one. Every system is a solution to a problem, but it introduces a new challenge. Upfeed, simple and cheap, but height limited. Downfeed solves the height issue, but it's expensive, complex, and super heavy. And pumped upfeed, it's the hero for weak pressure, but it's totally dependent on electricity. Seriously, burn this table into your brain and you are going to be golden for any questions the RA throws at you on this. And that's our deep dive into the 3 main water distribution systems. But it leaves us with a pretty interesting question, right? As we think more and more about sustainability and water conservation, which one of these systems is really built for the future? Is it the one that uses the least amount of electricity, or maybe the one that gives us the most control over usage? In the end, it just shows that understanding these basic forces, pressure and gravity, is absolutely fundamental. It's how we design buildings that don't just work, but are also smart, efficient, and resilient. Thanks so much for watching.